Okay, so here we are on our second type of question here for episode number 7. So this is 7B. And what we're doing today is we're going to determine or do a question where it involves calculating the initial concentration of a weak acid. Okay, so I've just put it up here kind of in shorthand, calculating initial acid concentration. So it should actually say of a weak acid because it might be slightly different. If it was a strong acid, hydronium equals the initial acid concentration because it's a 100% ionization. So you figure out the hydronium from the pH and it's the same as the acid concentration and you're done. Like, it's not that hard. This one's a little bit harder because it involves IRE tables and KAs and things of that nature. Okay, and it gets a little bit stickier. There's still some algebra that needs to be done. There's going to be a variable in there. So the question's already up on the board. So let's go to it. So the question says, what mass? Okay, so I didn't even ask what's the initial concentration. What mass of benzoic acid needs to be dissolved into 250 mils of distilled water? Okay, so pure water hasn't got any contaminants in it. It's just plain old pure water at 25 degrees, and that's key. 25 degrees means we're able to use the Ka of benzoic acid if we need to off the table. To create a pH or a solution with a pH of 2.47. Okay, so you know what you want it to finish at. You just don't know how much acid you put in to get there. So thinking of an IRE table, you know what you want on your E line, you just need to figure out what to put on the I line. Okay, so that IRE table, which is what you need to be able to use the K expression and calculate using Ka, those are in concentrations. So when you get an answer to the calculation you're going to do, it comes out as an initial concentration, which is moles per liter, of the acid in question, in this case benzoic acid. In order to get mass, we're obviously going to have to convert that concentration into moles by multiplying by volume, and then from moles to a mass by multiplying by the molar mass. Okay, so there's a bunch of steps that are going to happen at the very end, and we'll go through those it's a Chem 11, it's a practice of your Chem 11 skills. But first thing we're going to do is we need to do the Chem 12 part of it all. So let's write, as we typically do, let's write a chemical equation that shows benzoic acid acting as an acid in water. And then 2, let's do an IRE table, and then see what pieces we know, and we'll go from there. So benzoic acid. What is benzoic acid? So very few people are going to know what benzoic acid's formula is off the top of your head. So where do you go? Well, you could Google it. It'll be right there. But if you're not allowed to Google things during a quiz or a test, or in a scenario where your teacher's watching you like a hawk and they expect you to be able to figure it out, there's other sources at your fingertips. So source number 1 is typically your Ka table of acids, gives the names. Typically it does. And so benzoic acid is on the one that I use. It's right there. You just go down until you find benzoic acid. There may be, benzoic is because it comes from benzene, it's an organic compound, and so there may be a second name. So there might be the modern organic name like benzoic acid, but there might be an older form of the name too. It doesn't happen in this situation, but it could. So don't freak out if it's not immediately there. You just got to look up. Maybe there's a secondary name that people don't know about. Now, if it's not on there, acids come from, their names tend to come from what anion they're stuck to, right? So you know that an acid is an H stuck onto something. So benzoic acid is because an H is stuck onto the anion benzoate. And so you might have a table that has anions, and one of the anions listed might be benzoate. And you look up benzoate, and I'll just kind of show you what I'm talking about. Let's pretend you look up benzoate on your table of anions, and it gives you that. that means that's the formula of the anion. And so, like if you had sodium benzoate, you would have NaC6H5COO, kind of like acetate. Sodium acetate is NaCH3COO. It's one of those COO. It's an organic acid. So the organic acids, to make the acid, you put the H back on. Well, where do you put the H? Well, typically you drop that and you put the H at the end of the COO, and that's where it comes from. So organic acids always have that form. They come from the anion. So there's a couple ways that you can look it up, and there's a little bit of logic to it all. Sure enough, if you look it up on this, it's going to be there. It comes out, it shows you exactly what it is, and you don't have to put the H back on. So let's write the equation first. So CH, C6H5, COOH. Now, benzoic acid is not super soluble, so it's kind of hard to make it actually dissolve in solution, but we're gonna suspend that for a second, and we're gonna say it dissolves well. So it goes into solution, reacts with water, it forms hydronium, as all acids do, and C6H5COO minus, which was that benzoate thing, the conjugate base of benzoic acid. So, IRE table. What do we know? Well, we know to cross out the water because it's liquid. And liquids don't change concentration, so we don't include them in IRE tables, or K expressions, or calculations, or anything. So, what do we know concentration-wise? Well, let's take a look at the question. The question says, what mass of benzoic acid needs to be dissolved in a certain volume? So we don't know what that mass is. We're actually trying to solve for it. So the thing that we don't know is actually the initial concentration of the benzoic. We can't put anything in here other than, as you're going to see, it's going to be a variable. Now, you might see that right off the bat. You might go, well, it's clear that we don't know the initial concentration. Well, if we don't know the initial concentration, we can put an X there. So let's put an X there, because that's kind of the simplest thing. We don't know what it is. We know that these are 0. They typically always are, unless we have something weird going on. And during the reaction, it's going to go towards the zeros. So this is going to go up, and this is going to go up, and that is going to go down. What else do we know? We know the pH. So we know that the pH says 2.47. Remember from the last little one that I said, that when you measure the pH of a solution, you dip the pH meter in whatever and it reads it. But it's reading it at equilibrium already. Like it's already done its equilibrium business. Like you've made the solution, it formed an equilibrium. Now you've dipped the pH meter in. Now you're taking the equilibrium hydronium, because that's what pH is. So really when you take a pH, it's telling you that, and only that, the equilibrium hydronium. So the pH is 2.47. To get the hydronium, you're taking 10 to the negative pH. So we're taking 10 to the negative 2.47, which I need my calculator. I cannot do that in my head. If you can do it in your head, good for you. I don't know how you do that in your head. You can probably guess. So I've got 10 to the power of negative 2.47. And how many sig figs do I get? Numbers before the decimal don't count. Numbers after the decimal do count. So the 4 and the 7 are significant. The 2 is not. So I get 2 sig figs. So I have on my calculator 3.388 times 10 to the negative 3. 3.88. So I get 3 it's either staying as a 3 or going up to a 4. Since there's an 8 to the right of it, I get a 4. So 3.4 times 10 to the negative 3. Now, I don't particularly like Sorry. Fade to black. I have to change the time on that. I don't particularly like scientific notation. If I can take it out of scientific notation, I do. And so I'm going to take this out of scientific notation when I put it in my table. So 0.0034, 0.0034, 0.0034. So the E line is just completing that math. And this is pretty simple. Okay, so now I have a variable on the E line, which means I'm going to have to solve. And I need a Ka. So the K expression, the first thing you'll always write down once you've kind of filled in your E line with everything that you need, whether it's numbers or whether it's got variables in it, it doesn't matter. You're going to write down the K expression, which is the formula in chemistry. So the Ka equals the hydronium times, times the benzoate, the two products, over the concentration of the benzoic acid. Now I plug in what I know. So the Ka is off the table. Okay, so I pull out my table, and because we're at 25 degrees, and I did say 25 degrees, good. So benzoic acid at 25 degrees is 6.5 times 10 to the negative 5. Equals 0.0034 times, of course you could have written that just 0.0034 squared, over x minus 0.0034. Now, for those of you who could have anticipated mathematically that it might have been easier to do the math if the bottom of this fraction right here was just a plain old x, which, if you had labeled the equilibrium concentration of the acid as x, it would have made the math easier. You would have then had to remember that once you solved for x, you have to go back and add 0.0034 to go back to what the initial would have been. So as long as you can remember to do that, you can make the math easier on yourself by making an x on the E line, but you have to remember. Once I solve for x, I've got the I. Like, I've got the actual final initial concentration that I want to move on with. So I don't have to remember that. So if I've got a short memory, then maybe I'll do it the way that I've done it here. Okay? So now I do pull up my calculator, and now I have to do the algebra. So I'm running a little bit out of room, so I'm going to move over to here. So I have 6.5 times 10 to the negative 5 times x minus 0.0034 equals, and I'm just actually going to do 0.0034 squared. And I got 1.156 times 10 to the negative 5. And then I have to actually do the math here. So I multiply out this bracket. So 0.0034 times 6.5 times 10 to the negative 5. 2.21 times 10 to the negative 7 equals 1.156 times 10 to the negative 5. Okay, so I'm doing algebra, right? At this point, your math teacher would probably be a better person to kind of be walking you through all the steps in this thing. So I'm just doing algebra. I'm kind of assuming at this point in your grade 12 career, you can do this level of algebra. So now I add So 2.21 times 10 to the negative 7 plus 1.156 exponent negative 5 equals, so 6.5 times 10 to the negative 5x equals 1.1781 times 10 to the negative 5. And now I'm dividing by 6.5 times 10 to the negative 5. So x equals, which is the initial C6H5. So x is my initial C6H5COOH. Okay, and that's what this value is going to be. And it comes out to, let me just do it here, divided by 6.5, 10 to the negative 5. And kind of following sig figs all the way back. So I get 2 sig figs at this point. So I've got 0.18 molar. So this number right here, that initial concentration needed to be 0.18 in order for that solution to produce 0.0034 hydronium, which when you negative log it came out to a pH of 2.47. That's the concentration. That's not what the question asked me, but that's the concentration. So now to actually answer the question, the mass is going to be the concentration times the volume times the molar mass. Now, depending on how you've been taught how to do all of these things, I tend to do it from a unit perspective. And so dimensional analysis, it's called, where you cancel units and you end up with the final unit of your answer. So mass needs to come out in grams, so I need a grams per mole to start with. So my grams per mole of benzoic acid. I'm going to assume you can all do a molar mass, so I'm going to kind of do it in my head. So I have, chemical is actually C6H5COOH. So I've got carbon, I've got 7 of them, times 12 is 84. Keep that in the back of your head, 84. I have 6 hydrogens, they're 1 each, so I'm up to 90. Oxygens are 16 each. 2 of them, there's 32. So 90 plus 32 is 122.0. So 122.0 grams per 1 mole. And really, if you're struggling with something like a molar mass, make sure you email or contact your teachers. They can go through all of those things as well. So I've got 122 grams per mole. I need to cancel the moles, and so molarity is what I'm going to put in next. 0.18 moles per liter. And my moles cancel. If somebody asks you what density of solution you should have, well, here it is. It's grams per liter. And now I need to multiply by volume, which up in the question. So my final answer, if I do all of that math, I'm going to get the answer. Now, I've still got the unrounded value right here of the 0.18, so I'm going to use that because technically I haven't really changed anything. I can use this unrounded value and then round to 2 sig figs at the very end. So that guy times 122 times 0.25, which is milliliters converted to liters. And I end up with, to 2 sig figs, 5.5 grams. So this type of question, any question where you're asked for initial, you still need weak acid equilibrium, you need an IRE table, you need a K expression. And the unknown will be what the initial concentration is. Now, once you get an initial concentration, you can go to a variety of different things, right? You can go to masses, you can go to number of particles, you can figure out what volume of gas at RTP needed to be dissolved into the 250 mils of water. So there's a whole bunch of different things that you can do from there, but the initial concentration is key, and that's where your unknown is. Okay, so that's that type of question. Our next one is kind of an unusual one where you've got a really dilute weak acid, and it gives you kind of a strange phenomenon mathematically. So I'll show it to you so you're not freaked out by it, and you'll kind of go, oh yeah, that's kind of interesting and unusual, and it will remind you about what's already present in water. Okay, so we'll see you next time for that.